This is Cyberpunk 2077 running at about 180 FPS on the Nvidia DGX Spark platform, 20 ARM cores in our MSI EdgeXpert. Yes, this is an ARM platform running my entire x86, more or less, Steam library. It was not meant to do that. This is an AI monster. It has 128 gigs of memory. It is meant to be a platform for learning like Grace Blackwell and deploying from GB10 all the way up to GB300 on your desktop. It does a little bit of everything. It has ConnectX-7 networking, but now also you can run your entire Steam library on ARM. Like, they didn't port Cyberpunk to x86, and yet here we are, multi-frame generation, the whole 9 yards. It's, we're arming ourselves with the ARM platform, but there's more to it than that. We got to talk about the AI. We got to talk about inferencing. We got to talk about stacking up 2 of these and using nickel to do dual inferencing, 256 gigs on this platform. But I thought that would get your attention. Can it run Doom? Quite handily at 150 FPS. It's basically 5070 level performance, but don't buy this for gaming on ARM, even if you're really excited about ARM, but it can do it. Now, if you want to set up the gaming stuff, there's a full how-to guide for that on the forum, but that's not really what the point of this video is. One of the interesting things with this use case, though, is that you can very quickly hit the power and thermal limits with this platform when you're running this kind of a test. So this was a convenient way for me to see, hey, where does thermal throttling occur? And as I mentioned in my original DGX Spark review, this little thing was hitting some thermal limitations, and we may have seen some fallout from that on the internet at large. Now, I replaced the thermal material in mine, the one from Nvidia, with PTM 7950, using my lifetime supply of it from Linus Tech Tips. The PTM 7950, this is phase change thermal material. It's very good. It makes sense to repaste, old GPUs and things when you run into problems, but this was repasted from factory. Out of the box, the MSI EdgeXpert uses about 12% more power and is 10% faster. It can also sustain over 200 watts from the wall when running those kinds of gaming benchmark workloads. That is better than our reference DGX Spark. This is a metal case, it's gold, it's got the the plastic door on the bottom that lets you get to the Wi-Fi, and we did the 3D printable stand that you can download for this on the forum, which will give you a little bit better Wi-Fi reception, because otherwise all that metal, your Wi-Fi is on the bottom. This is a plastic case, but this is a superior thermal cooling solution by far. MSI has done a great job engineering this. I think it's a vapor chamber design for the cooler, and so that's why this is faster, 10% out of the box. Now, we're gonna link these two together a little bit later in the video, so I'll come back to that, but the MSI thermal design here is superior. If you're running an inferencing workload, that is, you load an AI model and you run things, you're mostly constrained by memory bandwidth. This wasn't news to anybody that was paying attention, but when this launched, some of the negativity around DGX Spark launching was that everybody expected better AI inferencing performance. Nevertheless, this has a ton of compute horsepower, as demonstrated by the ability to emulate x86 on the fly. These games are not designed for the ARM platform, they're designed for x86. And so this thing is translating using its ARM, it's 10 cores, it's got 10 big cores and 10 little cores, basically. And it's using its ARM cores to translate x86 to ARM on the fly, and it's doing a really nice job of it most of the time. There are some minor glitches and gotchas and that kind of thing. But that also means that more of the CPU is being stressed. We're using our memory bandwidth for the gaming side of it, like as if it's a 5070, but we're also using it for compute and everything else. And so in that, you're able to really see the difference between these two platforms. If you were using this purely for like NVIDIA's new FP4 format, which is really where the performance delta on this sort of takes off, and you can get some significantly better inferencing performance that is not as limited by memory bandwidth, then the rest of the system demands power in such a way that you may start to get into thermal limits, whereas the MSI EdgeXpert implementation of the DGX platform from Nvidia is doing a fair bit better. Now, out of the box, it comes with a version of Ubuntu that has been configured. Interestingly, with the update, I'm not sure if it's because I had to re-image my original Spark or anything like that, but in our platform here, it actually is Ubuntu Pro. Out of the box, you get your DGX dashboard. That's all the same. It's exactly the same software loadout from MSI as it is from Nvidia, at least on my test loaner unit from MSI. Jupyter Lab, all of that is basically the same. It's just a little bit faster because it has better thermal characteristics. This is a model of Nvidia's Grace Blackwell platform at the smallest scale, GB10. GB10 to GB300 NVL72. Nvidia is building the AI factory, and this is meant to be a lab/trainer for access to that lab. Inferencing performance is basically, it's limited by memory bandwidth, as I said, and so, as I also said in my original review of the DGX Spark platform, this is of the framework desktop. This is based around AMD Strix Halo. Strix Halo is, strictly speaking, is a mobile part, but it's a mobile part with high memory bandwidth, and so it has been repurposed for doing AI. And it is a scrappy little platform. It is amazing. I wouldn't be surprised if it is like the scene from the Iron Man movie where Obadiah is screaming at the engineers, is like, Tony Stark did this in a cave with a box of scraps. And it's not really, in fairness to AMD, it's not really like that. I mean, it probably feels like that if you're inside NVIDIA working on things, but the Strix Halo platform, it does inferencing. It happens to do inferencing best mostly through the Vulkan backend and not even like the ROCm backend, like ROCm being at performance parity with Vulkan when we're talking about non-CDNA architectures. Like, I'm already unpacking a lot of stuff. It's like CDNA versus RDNA, and it's like there's fragmentation in AMD's ecosystem, and like this does inferencing really well. It doesn't have a networking interface. It doesn't have anything else. If you want to spend half the money or less and just run inferencing and have a little AI box at home, the inferencing performance of this is basically equal to this from NVIDIA in basically every scenario except for one, and that is when you're using NVIDIA's special FP4 format. You spent about $8,000 for systems in this configuration, but the 200 gig interface from here to here, the way that you plumb that and deal with that in software, is basically the same as GB300, GBL300, NVL72. So from the very small scale to the large scale. There's a little bit of misleading stuff in that, though, in that the performance of some of the kernels in some scenarios in some Grace Blackwell configurations at the higher end are different, and so not all of the math kernel plumbing is there exactly the same from here to there, but that is some of the rough edges in the Blackwell launch that NVIDIA has very quickly rushed to correct. All right, so who is this for then? And we'll talk more about inferencing performance, because this versus this, that's an RTX Pro 6000. This is $8,000-ish dollars, $8,000-ish dollars. Yeah, so who's this for? This is for developers that are looking to participate in the entire NVIDIA ecosystem. You see, it's foolish, in my opinion, to focus entirely on the hardware aspect of it, because it is a larger conversation about the whole ecosystem. NVIDIA inferencing microservices and the AI factory and run AI, these are not just like the talking points that NVIDIA wants you to focus on. NVIDIA, I think, with the Blackwell, like the Blackwell launch was so ambitious that the cracks are showing in the foundation with like CUDA. Like a lot has actually gone wrong with the Blackwell launch and the Blackwell architecture if you pay attention. And most of that comes from a kind of Icarus factor where NVIDIA is flying too far, too fast, too close to the sun. A lot of the performance gains in what NVIDIA is talking about, I would sort of unjudiciously say that they're conflating hardware performance gains and platform gains and like engineering gains with stuff that they've done in software to remove precision. There are trade-offs that have been made where there are significant downsides to some of that. Now, NVIDIA's FP4, to their credit, they've done a lot of computer science, and there's RxV papers. They haven't just eliminated the bits and eliminated the precision that goes with that in a proportional way, i.e. 8 bits reduced to 4 bits is a 50% loss in precision for a 50% loss in bits. That is not actually reality from playing with it and from playing with DGX Spark the last couple of days. I didn't maybe connect the dots enough for some of you, because some of you are very hyper-focused on just, I want AI, a local AI in a box, a local AI helper. I only care about inferencing performance. If that's you, then you probably don't need this platform because you're probably not going to run your AI on this platform at scale or a larger cluster. This is for getting things, like you can do inferencing and training and fine-tuning locally on this platform. You are constrained by the memory bandwidth, but it's going to work just as well on this as somewhere else. And you are able to run that data locally, not in the cloud, not even in a private cloud if you don't even necessarily trust a private cloud. But when you set up your infrastructure here and you get it working here, if you need to scale it, you have a path to scaling it. This only has 96 gigs of memory. Some of you were probably already screaming at the screen and like trying to shove a Cheeto through your display. That's completely fine, totally fine. I've been there too. 96 gigs of VRAM. Each one of these has 128 gigs of RAM that is accessible to the GPU. It's the slower memory, like GDDR7, insanely fast, faster than a cheetah. It's like faster than Speedy Gonzalez, faster than, I don't know, is Speedy Gonzalez problematic in 2025? We can run a 256 gig model with our connection here, which, you know, you can use chapters to skip ahead if you're not interested in hearing me wax poetic. The performance is quite good. We can also compare performance against our Strix Halo machine. So like, yeah, no problem. Sure, let's talk about AI running here and AI running on the Spark, and then AI running on our RTX 6000. We could talk about that in an apples to apples comparison. But forget all that talk. That's not where I want to go with this conversation. I want your mind to be there, but I want you to pull back for a second and think about it in a different way. If you look at not VLLM's optimizations are almost entirely around things running on a GPU. And you look at llama.cpp, its origin story, and some of the offshoots of videos that we've done with like ikllama.cpp, then the RTX Pro 6000 can make sense in another buying scenario over the Spark for those inferencing conversations. And that is, yes, it only has 96 gigs of VRAM, but with llama.cpp and ikllama.cpp, and if you're using LM Studio or something like that, those are a little behind the curve. Those are not at the bleeding edge. Those fun GUI platforms are not at the performance leading edge for doing some of the stuff from the command line, the fun stuff that we do here at Level 1 Techs. You run some of the AI on your GPU, you can run some of the AI on your CPU. And so if you have a 4 or 8 or 12 memory channel platform that you're running your AI on and a sufficiently powerful CPU to take advantage of the memory bandwidth on that platform, then yes, you can really unlock some amazing things. You can build a system from 1 or 2 RTX Pro 6000s, which we have done, and have breathtaking, face-melting performance. And you're spending $8,500 per GPU. It's the same performance as a 5090, except instead of 32 gigs of VRAM, you have 96. Which, by the way, you can do this with a 5090 as well. Like, you can run stuff on a 32 gigs of VRAM on your 5090 and let it spill over into the rest of the system platform. That's what got me so excited earlier this year, because that is a kind of, egalitarian pleb level access for AI. You can run, like, it's a little tough to support GPUs on the Strix Halo platform, but you can mix like AMD Threadripper and AMD EPYC CPUs with Nvidia GPUs, and that mixed platform for AI, on some on CPU, some on GPU for home lab and use cases, that is completely reasonable and fine. The problem that remains with that approach is the ecosystem is not homogeneous. You're not going to rent cloud time on a platform that is set up like that. You're not gonna have llama.cpp with all the weirdo patches to make it go fast on CPU in the cloud. This is a cloud experience on your platform, running locally on your desk. And yes, the performance for inferencing and fine-tuning and all that will not set the world on fire, but for FP4, it is not bad. I was hoping for more, even with FP4, even with NVIDIA's special format, but with FP4, it's pretty good. We experienced that at Level 1. We did a 1-bit version of DeepSeek, thanks Ubergarm, that, that's from the Level 1 community, that is probably the best, if not one of the best, 1-ish bit per weight versions of DeepSeek on Hugging Face. And that means that you can run it in something that has 128 gigs. You can run it here, you can run it there, with a little bit of spillover into your CPU memory. You can run it wherever, but yeah, it's doable. All right, let's get to the benchmarks. Let's actually talk about the benchmarks and go through those and see how that shakes out. All right, so for benchmarking, it's really interesting. And if we start with the GPT OSS 120 billion, you can kind of get my point about the whole thermal situation. And keep in mind, my Nvidia reference Spark has been already repasted, as I said before. So, 1600 tokens per second versus 1729, 52, 15, 57. You can see that the MSI version of the Spark is a fair bit faster. In the neighborhood of 10%. It depends on what you're doing. Now, the other thing is that for inferencing, the thermal solution that Nvidia designed really isn't too bad. And I've got that blog post where it's like, oh yeah, 100 watts. Again, if you really stress out the Spark, it can get really hot, and then you start to run into thermal throttling. I get that a little bit with the ConnectX 7 NIC when I'm using the NIC and doing a lot of CPU horsepower thing or Steam or anything like that. This is the illustration. These are the numbers to back that up, because the MSI will sit here and do this kind of performance all day long, whereas the performance can get worse than this on the reference Spark depending on what you're doing, which is interesting. I have a feeling that Nvidia will probably correct that or ramp the fan speed or something like that at some point, but for now, it is what it is. Now, what about performance versus Strix Halo with the 120 billion parameter model? It's only going to use 60 gigs of VRAM. Well, so in order to do this, I want to show you a couple things. You've got the AMD toolbox. This is the AMD Strix Halo Llama toolbox. This is some rando. You're going to have to use this. And this builds the ROC, and this builds a llama.cpp backend with all of these options. This is what you need to do. Most of the time, Vulkan is going to be the fastest option when we're talking about Strix Halo, but there are a couple situations and a couple models that will run faster with the ROC and backend, and I'm super excited for that because that has not been the case for a long time. So we actually have a lot of other like if you're interested in like really deep dive Strix Halo stuff, we have a lot of other content on that, and it is a thing, but this is why I keep saying that it's not really an apples to apples comparison. If you're just strictly talking about inferencing, okay, yeah, maybe. But we also have reviewed like the GMK Tech Evo, and they have done some benchmarking on this, and you should check that out. The GitHub issue tracker for the I don't know how to pronounce that, the AMD Strix Halo toolbox from this amazing superhero that AMD should definitely hire and give a lot of money probably to, because they are a super productive individual or group or whatever producing all this fun stuff. There are benchmarks there, but there's also this on the llama.cpp from Mr. llama.cpp himself, who is also one of those super insanely productive people. And my benchmarks here are roughly in line. Look, there's Jeff Geerling. He check it out. He tried to run the network thing with these. It wasn't super fun, like building a cluster of these. But this is a similar performance to what you can expect. Now, the thing that I found when benchmarking this is that for very long context windows and long prompts, the Strix platform fell well behind. The Nvidia platform could be well ahead for long contexts and input processing across several different models, not just our GPT mixture of experts, but and not just the Llama models and everything else. The performance was it depended. The other thing that's interesting is the NVFP4 format is not widely available yet. If you look at the build.nvidia.com/Spark, you can quantize 8 and 16-bit models down to the NVFP4. There is a lot of misinformation right now on the internet about, like the MXFP4. That is the format of the GPT OSS that we have in this model and some of the benchmarks that we're talking about. And the performance of the MXFP4 is going to be very similar to the NVFP4. But what the NVFP4 is supposed to buy you is better accuracy, much better accuracy than the MXFP4. And there's kind of a movement right now on the internet that overshadows the actual innovation that Nvidia has done with their 4-bit format. But this 4-bit format is not supported yet by llama.cpp. And so when you run the benchmarks, sometimes you get in a situation where it's not an apples to apples comparison for accuracy and the accuracy of the output when we're talking about these 4-bit models and like Strix Halo and everything that's going on with Strix Halo, even to an extent with 8-bit. But so it's like you've got to run the benchmark, but then you also have to make sure that the output of the benchmark is just as coherent across platforms. And that can be tough to do with the state of ROCm on Strix Halo, because ROCm is meant to be cDNA, not RDNA, and it shows. But also even with like the Vulkan backend. And so it's like you've got kind of like the Vulkan RDNA, like you got to learn some platform specific stuff. Whereas over here on the Nvidia side, the platform, it's not completely free of the same sort of platform specific pitfalls. And NVFP4 is one of the things that I would point to for that, because some of these backend math kernel formats are not exactly the same from GB10 all the way up to GB300, and like even GB200 when we're talking about, you know, if you want to get into like the nitty gritty of like FP32 and FP64 performance, then there's a whole other conversation to be had there. But the performance here is as good as one expects for a platform that has 275 gigabytes per second memory bandwidth. And like I say, the performance of 4-bit versus NV 4-bit is going to be roughly the same, but the accuracy is what you get. So the trade-off is more, you didn't give up as much going to 4-bit to get the performance as you do in some of the other 4-bit formats. Oh, and I almost forgot. This is our output from running GPT OSS 120B with the ROCm backend on Strix Halo. And this is using the bleeding edge toolbox for Strix Halo. But keep in mind, this is GPT OSS 120B, and these are very respectable numbers, but the numbers and the comparison is going to be different depending on the type of model that you run. Llama and Granite, IBM's Granite, and Qwen and GPT OSS have different performance characteristics across both of these platforms. And just for the sake of completeness, we've got a few other models. Trying to do Strix Halo like for like, it took an inordinate amount of time because the Strix Halo ROCm backend was not perfectly stable. Most of the time I could reboot and it would recover, but I also wanted to test Gemma 3 12 billion parameter at Q4 and the Qwen 3 coder 30 billion parameter model. And you know, in some scenarios, the Strix Halo with the Qwen 30 billion parameter model can be a little bit faster, but anything that involves computation, the Spark is going to pull well ahead. And this is just LLMs. If we get into Stable Diffusion and we look at Stable Diffusion and image generation benchmarks, those are typically more compute bound. The lack of memory bandwidth has less of an outsized impact on performance. Then Stable Diffusion type performance in the benchmarks will be significantly better. So keep an eye on that forum thread, because I'm going to update it with some more numbers. But you know, early look, anything that's computation bound works really well. We also got Nickel and being able to run, you know, 2 Sparks at once, and how does that scale? And it depends on the software platform that you're using. But I'm also happy to report that putting together a Python program here, thank you, you know who you are, worked really well. It's like setting up Nickel and then being able to run that and do distributed benchmarking, and all of that worked exactly the way that you would expect. I unfortunately went down a bit of a rabbit hole trying to get Rickle. That's the AMD's version of Nickel, working between 2 Strix Halos, even adding, you know, my dual 50 gig or my 50 gig InfiniBand setup. Like, it doesn't, like, it's not really a thing that's working properly. It hasn't changed much since Jeff Geerling's video on trying to set up multiple AMD Strix Halo for something. And it doesn't even, like, even if you got it working, it's not going to work the same way there as it does in the data center. Whereas on these GB10s with this Nickel setup, it is basically the same as like the big, you know, GB200, GB300 setups. So depending on what you're doing, you can get scaling. Now, for my testing out of the box, I was getting about 1.7x running these like 70 billion parameter models. But the name of the game here is not to be able to run a 256 gig model. What you're supposed to do, or like how this is supposed to work, is that you're running a fleet of agents. And so you have this idea of agentic AI, where you have, maybe you're using GPT OSS 60 billion or 120 billion as like a supervisor model, and then you have these other models that are off doing things. Maybe you want to experiment with DeepSeek OCR, or maybe you're using Qwen 3 for picking text, doing text recognition out of images, and you have these specialized workflows. Well, Nickel makes it easy for you to do that, and that works really well. If you do want to scale to where that you have one AI running across multiple machines, or and you've got some layers on some machines, some layers on the other. The absolute best I could get was about a 1.7x scaling, but the spread on this was like 1.3x, like 1.25x, 1.3x to 1.7x, and I don't have a lot of mileage, a lot of experience with nickel, so I'm still working on this. Keep an eye on that forum thread for more information, but it is working, and it is working well, and in terms of like inter-Spark communication, and at a ridiculous bandwidth, especially on the MSI side. MSI has done a really nice job with their platform, so yeah, nickel is legit. TRT LLM inferencing running on dual Sparks. Yeah, Nvidia's walkthrough here is pretty easy to do. The only thing that's really disappointing about this is that it's not really like InfiniBand or any really exotic technology. You can do this with anything. It's just Docker Swarm. Setting this up, you know, I've got the physical QSFP connection, passwordless SSH that we have from the nickel tests. And yeah, scaling factor depends on the model and the stuff that you're running. I can get scaling here as good as 1.8x. But I think this probably deserves its own video, its own question. So if this is something that you're working on, or you're running this same kind of thing, not necessarily even with Sparks, but you know, TRT LLM for inferencing across multiple machines, then hit me up in the forum and let's see what we can get going with Sparks. My ultimate goal here is maybe to sort of off-label, off-grid, set up 3 or 4 Sparks and a little mini cluster. Well, you can do 3 Sparks with each Spark directly connected to every other Spark, and that is a thing that works fine on Linux. All the routing, plumbing, and everything else is there for that. But this is pretty easy. Generate a config file, download the model, save the model, validate the API server, and then you're good to go. There's a cluster of Sparks here. Now, multi-Spark. How do you do multi-Spark? At build.nvidia.com/Spark, they have all these recipes and how-tos. You should definitely check that out. Even if you don't have a Spark, you can do that today. You can do that on a 5090, you can do that on a 4090, 3090, 24 gigs of VRAM. You can do all of this stuff today if you build a Linux machine around that. Nothing is stopping you. You don't have to spend $4,000 on hardware if you're just curious about this. One of the examples there is getting this thing up and running with your ConnectX 7 and NCCL for distributed jobs and workloads and that sort of thing with this. And it just works. You plug in the network cable and you're good to go. And that is mind-blowing. All right, so bottom line, if you're considering getting one of these for having like a home AI appliance, not for you. If you work on Grace Blackwell stuff or Nvidia stuff at scale, or you came up on something like a V100 cluster, or you're upgrading from like a V100 cluster, or even the old Ampere generation stuff, and you're getting your toe in the water with Grace Blackwell, or maybe you're in the queue to get some Vera Rubin stuff, then yeah, investing in this and having your team have access to this makes a lot of sense. If you're working on a startup and you need a model and you want to run stuff locally and get stuff running locally before you rent cloud time, then yes, this makes sense for you. If you're going to participate in the NVIDIA ecosystem, which I think the NVIDIA ecosystem is more important than the hardware. The hardware, like after Grace Blackwell, NVIDIA knows that they're going to face intense competition as well, and their differentiator had better be their software platform, ease of access, and everything else. What CUDA was for CUDA, what CUDA did in the past, CUDA cannot do in the future. But what NVIDIA is doing with NVIDIA inferencing microservices and Run AI and like the whole ecosystem, Omniverse, and like just looking at like the robotics side of it and the biosciences side of it and all of the places that NVIDIA is branching out, they're building a foundation that is like CUDA and will do what CUDA has done for them in the past, but everybody that is focused on inferencing performance is missing the boat because of all the other interesting stuff that's happening. And so this is your toe in the water to give you the CUDA ecosystem plus all of the other stuff. And you'd be crazy to leave all the other stuff on the table and just learn about CUDA with this platform. Like you could just get a gaming GPU. You don't need to spend, 3 or 4 grand. Bottom line, that's who it's for, that's how it works, and depending on what your interests are and your goals, there it is. I went to this level 1. If you have any questions or comments, or I got anything wrong, or you want me to elaborate on anything, join us in the community. We have a community of smart people. Mostly. I love you all. All right. Thank you for watching. Thank you for hanging out. If you have any questions, you can find me in the level 1 forum. I'm signing out, and I'll see you there.